This video is to try and help with both the question 6s from the homework. Thinking on this question as I do it rather than just the answers on the mark scheme, in case that helps. Sort of model through how I would tackle this if it was a real exam. So reading the information, I know this is a question about the electromagnetic spectrum and I've been given lots of bits of information. So the first thing I'm going to do is just remind myself and think about that core knowledge of what's in the electromagnetic spectrum. And of course, in my head I'm singing the song, but I'm not going to subject you to that. Radio waves, no, I'm really not going to subject you to that. There we go. So radio waves, microwaves, infrared, visible light, ultraviolet, X-rays and gamma rays. So these are the lowest frequency down here at radio waves. These are the highest frequency up here at gamma rays. And so looking on the table just at the frequencies, this is the highest frequency and this is the lowest frequency. So I'm just going to check that ties in with the other information I know about radio waves and gamma rays first. So for this high frequency, gamma rays are indeed used in medical scanning and they're produced, their nucleus of an atom is changing, it's radioactive, it's giving out gamma rays. So I am absolutely confident that I know this one is gamma rays now. So I can write gamma in there. And for the communication, radio waves are definitely used for communication and they are indeed produced by oscillations in electrical circuits. So I'm absolutely confident I've got my radio waves one right. So I've started with confidence and then the trickier ones to think about come after when I know I've already got half the marks basically. So next I need to think about, I'm going to go high wavelengths next. So if I think about this 10 to the 18 compared with 10 to the 16, these are a lower frequency, but they're not that much lower. So I'm up in this top end. Ultraviolet is never used in medical scanning. So I'm kind of pretty sure at this point it's going to be X-rays. And X-rays are indeed to do with the electrons changing their orbits. So I am going to go X-rays and feel fairly confident that I've got that one right. Which leaves me with the last one to think about. So this is down at the lower end. 10 to the 14 is my second lowest frequency in this table, but that is quite a long way away, 10 to the 6, 10 to the 14. So although this is a low frequency, it's quite a lot higher than the other frequency we were looking at for radio waves. So communications wise, microwaves are used and visible light is used in optical fibres and things, and those microwaves are just too close. I'm thinking it's not going to be them, it's going to be these. So let's check what other information I'm told. They are indeed, visible light is produced when electrons are excited to higher levels and drop back down and release the energy as visible light. So I am now happy with my last answer. So that's probably taken me longer than 4 minutes to answer because I've been explaining my thinking as I go, but I would spend 4 minutes for those 4 marks and be absolutely sure I'm getting them right as I have a go. I hope that showed you how to think about it. So sometimes, even when you see the mark scheme, if you're not happy with your maths, sometimes the mark scheme doesn't help either. So I'm going to model through this example for you. I have pre-worked this one out so that you haven't got to wait while I type numbers in a calculator, but I'm going to show you exactly how I would think through this question. So the speed of light I'm reminded of, and that's a familiar number to me. The wavelength of ultraviolet light, I am being told here, is 360 nanometers. So nano is 10 to the minus 9. So I've got 360 times 10 to the minus 9 meters, which you could change, but I'm just going to leave it as 360 times 10 to the minus 9. It's the frequency I'm trying to find, so I need to recall the correct equation. The speed of a wave is its frequency times its wavelength. I this time know its speed, so 3 times 10 to the 8 goes in. Its frequency I'm trying to find out, so I'm going to leave the F there for frequency. And they have told us the unit of hertz there. I haven't got to recall it on this occasion. The wavelength is 360 times 10 to the minus 9 to make sure I've got it in those standard units. So I could draw a triangle here, and that triangle would lead me to the same thing as if I use the balance method. So if I divide both sides by 360 times 10 to the minus 9, these ones cancel to leave me with f is equal to 3 times 10 to the 8 divided by 360 times 10 to the minus 9. And when I worked that out on my calculator, I got 8.3 recurring forever times 10 to the 14 hertz. So I would just put 8.3 times 10 to the 14 as my final answer here. So if you did want to use the triangle, what you would have done with your triangle is you would have said that 3 times 10 to the 8 up here was equal to frequency times the wavelength of the 360 times 10 to the minus 9 here. Then to find the frequency, you cover that over and it's showing you the sum that you need to do. I hope that's helped if the mark scheme didn't. Graph question, let me try and explain again how I would see my way through it if I was in an exam. So reading the question first, it's all about light being given out by a star and outer layers absorbing the radiation. So I'm interested in analysing this graph. I'm being asked to describe how the intensity, and the intensity is here on the y-axis, and it's increasing. It's intensity that's increasing as you go up the y-axis, and how that is affected and related to the wavelength. So the wavelength's here in nanometers, and the wavelength is getting longer as we go along the x-axis there. So the first thing I'm going to do is look at this general pattern, because it is general. I can't say anything exact and specific when I'm talking about the pattern here. But between the start of this graph here and this point here, in this region of the graph, as the wavelength increases in length, the intensity appears to be increasing. And then from this peak point here, so that's your peak, and from that point there, it's pretty much the same all the way up to about here, about 550 nanometers. It's pretty much the same intensity, even though the wavelength is getting longer. But then after that point, this third section is where, in general, as the wavelength gets longer, the intensity appears to be decreasing. So with my head around the idea of what the graph is showing me, I would finish up with an answer, something like, as the wavelength increases, the intensity increases generally up to a peak at around 400 nanometers. The intensity remains fairly constant from 400 to 550 nanometers, but there are several dips in the intensity at specific wavelengths, and that happens throughout this range. After about 550 nanometers, the general pattern suggests that the wavelength, as it increases, the intensity is decreasing. But there are these specific wavelengths at which the intensity sharply dips. I hope that's enough to get the marks. There are only 2 marks. I think I've probably been very thorough there. There is another question 6 in this homework, 2 question 6s. That's because by choosing question 6 here, both higher and foundation students are getting experience, because these questions are pretty much the same on the 2 papers. So they are early questions for the higher tier, but they are near the end of the paper for the foundation tier. So for our homework practice, they're ideal for our class where we've got students who are thinking about higher and foundation all within the same group. So in this question 6, as I read the question, I read that this teacher's demonstrating their toy car and their sand. It actually works quite well. But the key thing I'm reading, as I read, I'm thinking the car slows down as it enters the sand, and that means it will bend towards the normal. And that's the key thing that's jumping out at me as I read this question. So when I am then asked to draw an arrow on the diagram to show the car as it moves, I'm then going to draw my normal line in, and I don't need to do that accurately with a protractor for this 1 mark here, but that is 90 degrees to that surface. So there's the surface and there's my 90 degrees. And if the car didn't change direction, it would carry on up here, wouldn't it? However, it does change direction because it's going to slow down, and therefore it will bend towards the normal. So my final answer to that 1 mark is going to be there. Now, explaining why this is a useful model for refraction. Well, the wheels on the car are representing the side of each beam of the light. Light slows down when it enters glass, just like the car is slowing down when it enters the sand. So that's a good model. But it's more than that, because light would refract because one side of the light is slowing down before the other side, and therefore it bends towards the normal. The car is modelling this really well, because as one of the front wheels hits the sand before the other one, the one on the right hand side hits the sand before the left hand side does, that causes the car to slow down and skid towards the normal. So the car is changing direction in a very similar way to light. The last question we're going to have a look at in this video is part B, part 1. So we're being asked about the prism here and the light moving through the prism. Sunlight is white light, but white light is really a mixture of those different colours of light we see in the visible spectrum: red, orange, yellow, green, blue, indigo and violet. And each of those colours of light have a different wavelength. When the white light enters the glass, because it's specially cut the shape of this prism, each wavelength, each colour of light gets refracted, but they get refracted by different angles. And that's because they're slowed down to different speeds through the glass. So red has the longest wavelength. It slows down the least. It's refracted the least through the smallest angle. Violet has the shortest wavelength of the visible spectrum. Violet light slows down the most, and therefore it's refracted through the biggest angle. And the colours in between are slowed down and refracted somewhere between that fastest and slowest, that range. I hope that helps if the mark scheme didn't, and I hope the video has been useful if you found parts of this homework tricky.